Hey kids, this is Miss Schultes, and you should have your packet in front of you that says Chapter 7, Energy. Standards covered 2A, 2B, and 2C. Let's begin to read. Conservation of energy. You have heard the term conservation of energy before. It is usually used to describe the effort to save energy, like when your parents tell you, turn off the lights when you leave the room. Coaches are saying the same thing to an athlete when they tell her to slow down and conserve your energy for the end of the race. When scientists talk about conservation of energy, they are talking about something a little different. They're talking about an important characteristic of energy. Energy may be transformed, changed, from one form to another, but in the end, you always end up with as much energy as you started with. We'll put a pin in that. Let's pause right there. That is extremely important. Energy may be transformed, changed from one form to another, but in the end, you always end up with as much energy as you started with. It may not be the same kinds of energy. Some of it may have escaped the area that it started in, but the total amount of energy remains the same. This characteristic is often stated as the law of conservation of energy, which simply says that energy can neither be created nor destroyed. Now, that's a law or a rule, so I'm going to choose to highlight any law or rule in yellow. The law of conservation of energy. Energy can neither be created nor destroyed. When we use energy, it doesn't disappear. We change it from one form into another. Forms of energy. Energy can be found in many different forms. Some examples of different forms of energy are light, heat, sound, and motion. Any of these may transform. It is called an energy transition. For example, a car engine burns gasoline, converting the chemical energy in gasoline into mechanical energy that makes the car move. Although there are many forms of energy, they can all be put into two general categories: kinetic and potential energy. Kinetic energy is energy of motion. Kinetic energy is energy of motion. The kinetic energy of an object is the energy it possesses because of its motion. To put it another way, it's energy that has the ability, because of its motion, to act on something else and move it somewhere. When we think of the word potential, we usually think about how something or someone could do something if certain things happen. I'm repeating that. When we think of the word potential, we usually think about how something or someone could do something if certain things happened. For instance, have you ever heard something like this? Albert plays baseball so well. What potential? So at this point, you should have the first page, and you may have some other things highlighted. Conservation of energy is right there in orange. So I think probably the fact I have that sentence, but I didn't highlight the word. So conservation of energy. There was something else that stood out to me. It wasn't really a law. It was an example. Where was it? The gasoline and the car. Going to go back there. Okay. Sorry. Some doofus head has put tape on this highlighter and I'm sitting here trying to get it off. Don't be messing around with the stuff in the classroom while I'm not in the room. There you go. Okay. Here it is. Some examples, different forms of energy. And then we go down here. A car engine burns gasoline, converting the chemical energy in gasoline into mechanical energy that makes the car move. That's one specific example, and whenever you're taking a test or you're being asked questions, sometimes you're asked which of these is an example, or what happens when you provide fuel to a car. You would need to know that the chemical energy in gasoline is transferred, or the energy transformation is chemical to mechanical that makes the car move. All right, so moving on to the next page. Now, you see a chart there where at the top of the page it says kinetic energy. So it just told you at the bottom that all forms of energy are separated into two categories, kinetic and potential. So here we're looking at kinetic energy, forms of energy that are kinetic or depend on things moving. Mechanical energy, that's wind or a bicycle. Those are examples. Think of a windmill. The motion of a windmill is mechanical energy. The hand crank generators that some of you were working with, those were mechanical energy. Thermal energy, that's your heat, your fire, your friction when you rub your hands together, or friction in a machine. Thermal energy, why is it considered kinetic? And I think we're going to read about it in a minute. But remember, particle movement determines the temperature. That's your thermal energy. Radiant energy, that's light and X-rays. Sorry, I have a twitch in my hand. So let's go ahead and continue reading here. Stop playing video games. You're wasting your potential. Well, potential energy is not exactly about your future. It's more about the future of an energy source. The term potential energy means the stored energy in an object due to its position or composition. In other words, the object could exert this energy if something happened. Let's look, for example, at what happens when an archer pulls the string of a bow backward with an arrow. The more the string is stretched backward, the more potential energy is stored. All that has to happen to convert the potential energy in the bow into kinetic energy is for the archer to let go. Let's take a closer look at some forms of kinetic and potential energy. Before we do that, I'm going to make sure that you have some things highlighted here. And we've got the term potential energy means the stored energy. Potential energy means the stored energy in an object due to its position or composition. Just think about that bow and arrow. The archer pulls the string back with the arrow on it. And the farther it pulls it back, the more it is stretched back, the more potential it has. And the only thing that has to happen is let go. And then the arrow starts to move. There's your kinetic energy. So let's continue reading. Kinetic energy. Mechanical energy is the energy an object has due to its motion. This kind of energy allows one object to apply force to another object and make it move. In figure 7.1, a naughty cat is applying a force by swatting a vase. The cat is using mechanical energy. There's your cat swatting the vase. Mechanical energy. So the cat is using its bones, muscles, joints, and its legs to swat the vase over. That's mechanical energy. So if you're a baseball player and you hold the baseball bat and you swing the baseball bat to hit the ball, when you swing the baseball bat, that is considered a form of mechanical energy. You're using mechanical energy, your body, movement. So, mechanical energy. Mechanical energy is the energy an object has due to its motion. Allows one object to apply force to another object and make it move. Okay, electrical energy. Electrical energy is energy resulting from the movement of electrical charges. Recall that atoms are made of subatomic particles called electrons, protons, and neutrons. Applying a force, like friction or voltage, can make some of the electrons move from atom to atom. The movement of these electrons is called electricity. Static electricity and lightning are examples of electrical energy. So over there you see 7.2, electrical energy, there's your lightning. So, electrical energy, you need to remember, it's not all about the wiring in your home. Electrical energy exists anyway. The wires in our homes, we just figured out how to contain the movement of electrical charges to our benefit so that we do have electricity, electrical energy in our homes. Electrical energy is energy resulting from the movement of electrical charges. Atoms are made of subatomic particles called electrons, protons, and neutrons. Applying a force, like friction or voltage, can make some of the electrons move from atom to atom. The movement of these electrons is called electricity. Static electricity and lightning are examples of electrical energy. So, electrons moving from atom to atom, that's electricity. Got it? Now, go back up here to the chart. Let's look at some of the differences in kinetic and potential energy. Kinetic energy, we talked about mechanical energy. Mechanical energy can be seen in a machine, a windmill, a bicycle. Thermal energy, that's your heat or your cold. When the particles in a substance speed up, then the temperature goes up. When the particles in a substance slow down, the temperature is going down. Radiant energy, that's your light, your X-rays. Radiant energy is from the sun. Radiant energy and X-ray, when you go get an X-ray of your broken arm. Electrical energy, we just read about that. Lightning and electricity. Radiant energy, talk about the rays of the sun. Those are moving, and X-rays are actual movement. And then electrical energy, that's the movement of electrons, movement of electrical charges. Sound energy, thunder, sonic booms. Sound energy is the movement of waves. Okay, and some people refer to the radiant energy as light energy, so light waves. And we'll talk more about waves later. Potential energy. Remember, that's your stored energy. Gravitational energy, that's your H1 in IXL, guys. Gravitational energy, skydiving, and a water dam. I want you to think about how that's gravitational energy. Elastic energy, compressed spring, stretched rubber band, that archer with the bow and arrow. Elastic energy, the more you stretch it, the more potential energy it has. Chemical energy, a match. When you look at a match, a matchbook, a box of matches, when you strike a match, that end of that match, it is made up of a chemical that has a reaction and it's combustible. So that chemical energy, there are chemicals that are on the end of that match and it reacts and catches fire. So that's chemical energy that has the potential to react or catch fire. Gasoline is another form of chemical energy. When you eat food, that food that you eat is chemical energy in going into your body. Your body uses that food and it's chemical energy to provide your body with more mechanical energy. Nuclear energy. Nuclear energy is potential energy. Radioactive elements, stellar energy from the sun. So that's stuff that we don't really want to have to deal with. Nuclear energy is potential energy. It is real. And no, we don't want to have to deal with it. Okay. Let's talk about each one that were in the chart. Radiant energy. Radiant energy is energy that travels in electromagnetic waves, like that of the sun. In a vacuum like space, electromagnetic radiation moves at a speed of 3.0 times 10 to the 8th power meters per second. Since that is a very high speed, you can infer that electromagnetic radiation carries with it a lot of energy. It does. After all, the sun heats our whole planet with its radiant energy. Other examples of radiant energy are visible light, X-rays, gamma rays, and radio waves. Let's see. Radiant energy. Radiant energy is energy that travels in electromagnetic waves. Radiant energy. And we said earlier that that is the one that you've always referred to probably in elementary school as your light energy. Electromagnetic waves. Electromagnetic radiation moves at a speed of 3 times 10 to the 8th power meters per second. And I assume that's meters. I think it's meters. Since that's a very high speed, you can infer that electromagnetic radiation carries with it a lot of energy. The sun heats our whole planet with its radiant energy. Other examples of radiant energy. So here's examples. What did I highlight? An example. Example was green earlier. Examples of radiant energy are visible light, X-rays, gamma rays, and radio waves. Okay. Now, Thermal energy. Thermal energy is the internal energy in substances. Think of this as the movement of the atoms and molecules within a substance. This movement often generates heat, which is why thermal energy is often thought of as heat energy. Thermal energy always moves from hot, high energy, to cold, low energy. We will discuss this more in Chapter 8. That's talking about Chapter 8 in this little book that I got this paper from. So, thermal energy is also thought of as heat energy. And something that you need to know, thermal energy always moves from hot to cold, from high to low energy. The movement of atoms and molecules within a substance. Sound energy. Sound energy is the movement of energy through substances in compression. Okay, I think I read that correctly, but I'm going to start over again because I stumbled. So right there, sound energy. Sound energy is the movement of energy through substances in compression have to travel through a medium like air or water. Sound is produced when a force causes an object or substance to vibrate. When this happens, the energy is transferred through the substance in a wave. Sound moves more quickly in denser materials, like solids, than in less dense materials like gases. So I'm going to go back up here. I think there's something wrong here, or a typo. Sound energy is the movement of energy through substances in compression. Sound, I would say sound waves. Sound waves have to travel through a medium like air or water. There's a parenthesis right there, but there's not one wherever it was supposed to start. So I'm like picking apart this right here. It's like sound waves have to travel through a medium like air or water. Sound waves have to travel through a medium like air or water. And I'll say a couple of things about that. Sound energy is the movement of energy through substances in compression waves, maybe? We'll look that up a little bit more. Sound energy, I want you to think about this. When an astronaut, if you see astronauts with their suits on and you've seen them out like on the moon, or you watch a YouTube video of astronauts, they can see each other. The reason one astronaut can see another astronaut is because light waves are there, and if there's light waves, that's what allows you to see something. So sound needs a medium to travel through, like air or water. Well, there is no air on the moon. So when one astronaut is standing there on the moon and speaking to another astronaut on the moon, they can't just talk and hear each other. The sound waves have to have something to travel through. So they talk through a radio, okay? That's going to be kind of hard for you to comprehend, but think about what it says here. Sound is produced when force causes an object or substance to vibrate. If there's nothing to vibrate, then you're not going to hear anything. Right now, whenever you hear that knock, you're hearing it through the air in the room. The air is a gas. When you put your ear down to the table, and I'm actually doing it right now, and then you knock on the table, that knock, when you put your ear down to the table, is way louder. That's because sound travels better through a solid, like the table, than it does in the air, which is a gas. So you do need to know that. I'm gonna grab that right there. Sound moves right there. Sound moves more quickly in denser materials like solids than in less dense materials like gases. So I would put a note there like example, knock on table. Okay. Potential energy. Elastic energy is the energy stored in elastic materials as the result of their stretching or compressing. Elastic potential energy can be stored in rubber bands, bungee cords, trampolines, springs, an arrow drawn into a bow, etc. So elastic energy, your stretch energy. So when you pull that rubber band back, that's your stored elastic energy. Energy stored in elastic materials as a result of stretching or compressing. So remember, it could also be compressing. So if you squish something down, it's got that potential to spring back up. Chemical energy. Chemical energy is energy stored in the bonds of atoms and molecules. It is the energy that holds these particles together. Oil, natural gas, and propane all have stored chemical energy. Humans harness this energy by burning these materials. Batteries are another example. Very important that you remember that batteries are another example of chemical energy. I'm going to go ahead and grab that as an example. Oh, that's oil, chemical energy, natural gas, propane. Those are all stored chemical energy. All right, what was the definition of chemical energy? Chemical energy is energy stored in the bonds of atoms and molecules. And examples of chemical energy are oil, natural gas, propane, batteries. And remember, the food you eat provides you with your body with chemical energy. Okay. Nuclear energy. Nuclear energy is energy stored in the nucleus of an atom. It is the energy that holds the nucleus together. It is released when a nucleus is split apart or when more than one nuclei are combined. Nuclear power plants split the nuclei of uranium atoms in a process called fission. The sun combines the nuclei of hydrogen atoms in a process called fusion. Scientists are working on creating nuclear fusion energy on Earth because the energy put out by a fusion power plant would be much greater than the nuclear fission power plants we have today. Okay, nuclear energy is energy stored in the nucleus of an atom. And very dangerous if in the wrong hands. Nuclear energy is energy stored in the nucleus of an atom. It's the energy that holds the nucleus together. Okay? And you're given a very, very specific example here. Nuclear power plants split the nuclei of uranium atoms in a process called fission. Fission is split. The sun combines the nuclei of hydrogen atoms in a process called fusion. Right now, the power plants that we have work with nuclear fission. Scientists are working on creating nuclear fusion energy on Earth. Okay. Gravitational energy. Gravitational energy is the energy of position or place. Gravitational energy is the energy of position or place. For instance, if you saw a boulder resting at the top of a mountain, it would contain a great deal of gravitational potential energy. When water is held behind a dam in a hydropower plant, it has a great deal of gravitational potential energy. So we've got a couple of examples here of gravitational potential energy. The boulder at the top of the mountain and water being held behind a dam in a hydropower plant. Those are examples of a lot of gravitational potential energy. All that it would take for the potential energy to be converted into kinetic energy is for the dam gates to open. The gates on the hydropower plant, the dam in a hydropower plant, if those gates open, that water flows. That's your kinetic energy, the water flowing. So gravitational potential energy. So that right there helps you with IXL H1. Okay, moving right along. Kinetic and potential energy conversion. Think back to the early chapters of this book. You haven't read the book. We'll get to it later. When we made you aware that you had been a scientist practically your whole life. The example we looked at was when you threw a ball downward with varying amounts of force to see how it affected the height of the resulting bounce. So you throw a ball. The harder you throw the ball, it springs back up more. Okay? So get that idea in your head. 1, you threw the ball down. 2, it hit the ground. 3, the ball sprang up from the ground, launched into the air. 4, at its maximum bounce height, the ball reversed direction and began to fall. 5, the ball fell toward the ground. So here's what happened in scientific terms. After the ball left your hand, in step 1, it was moving, so it had kinetic, mechanical energy. When it hit the ground in step 2, it got flattened out or smashed. Although as scientists, we should use the technical term that the ball deformed. You can see this in figure 7.6. Oh, that was the one where the ball bounced and you can kind of see it squish down a little bit. Yeah, right there. The elastic energy. The ball right here, it goes down. So right there is where the ball kind of squishes to the ground and then it springs back up. Okay. So After the ball left her hand in step 1, it was moving. So it had kinetic mechanical energy. When it hit the ground in step 2, it got flattened out or smashed, although as scientists we use the technical term the ball deformed. You can see this in figure 7.6. The deformation resulted in the ball acquiring stored elastic energy. It then bounced in step 3. As it traveled upward, it again had kinetic mechanical energy. Eventually, it slowed down in step 4. At this point, the kinetic energy was being converted into potential gravitational energy. When the ball reached the peak of its journey upward, for a split second, all of the kinetic energy was converted into potential energy. That split second that it reaches the very top, as high as it's going to go, and then it begins to fall back down. As the ball fell back down toward the ground in step 5, the potential energy was gradually converted into kinetic mechanical energy. The closer the ball got to the ground, the less potential energy and the more kinetic energy it had. That's a lot from one ball being thrown to the ground, hitting the ground, bounce back up, and then fall back down to the ground. You need to be able to make sure that you understand how that. So right here, when you throw that ball down, that's your mechanical energy. That's your kinetic. Mechanical energy. It hit the ground. When it hits the ground, it gets flattened out. So it's deformed. So it's squished down. That's your elastic energy, stored elastic energy. So potential. And why is it elastic? Because it was squished. The ball sprang up from the ground, launched into the air. So that's your kinetic mechanical energy again. At its maximum bounce height, so when it gets to that point where it's right at the top of its arch, and then the ball is about to start coming back down, so it bounces back up, it's as high as it's going to go right there in that split second, and then it starts going back down. When it reaches that tip top point, what does it say? At this point, right at the very top, the kinetic energy was converted in potential gravitational energy. And then we have here, the ball fell to the ground. So as it's falling back toward the ground, it is converted into kinetic mechanical energy. So kinetic mechanical, it's falling toward the ground. And the closer the ball gets to the ground, the less potential energy, the more kinetic. So it's kinetic mechanical again. So when it's at the top of its fall, it's got a lot of potential, and then as it gets closer and closer to the ground, the potential is decreasing and the kinetic is increasing. It's a lot for one ball drop. Okay. Thermal energy loss. Oh, and look, one more sentence about the ball. Each time the ball bounced, this process would repeat itself. Thermal energy loss. So this is the page you should be on. Energy conversion from one form to another happens constantly. It is happening in every move you make and every electrical appliance you turn on. But energy transfer is not efficient. That means that some energy is lost during nearly every transition, but it's not really lost. It's actually just a side conversion into thermal energy. Thermal energy is often the result of friction. That is, things rubbing against each other. Table 7.2 shows some examples. We'll take a closer look at thermal energy in the next chapter. Okay, so let's definitely make sure that we know these examples and that we know what we're talking about here. Turning on a battery-powered flashlight. Okay, the flashlight works because of a battery. The battery is made up of lots of chemicals. So that's your chemical energy in the battery. You could even go so far as to say you've got to turn it on, so there's a little bit of mechanical. Doesn't mention that though, it's okay. Battery power, so it's chemical to electrical, and then we see the light. There's something electrical happening with the wiring, then the light energy. Now, how is some of that energy lost? Because you know the battery's going to go dead. And you also know that the flashlight bulb, if it's, a regular flashlight or a really good flashlight, some of the energy there is transferred into heat. So you're going to lose, which you don't lose it, but heat from the flashlight bulb, okay? Or even from the wiring inside or from the chemicals inside, okay? And that makes me think of your cell phone. Whenever your cell phone gets really hot because you've been using it a long time, that is chemical energy and electrical energy right there. And it's losing its energy from that heat too that's being produced. Turning the turbine in an electric generator. A turbine in an electric generator. Mechanical to electrical. Heat from friction within the generator. Any generator has multiple moving parts. So if it's got multiple moving parts, then you definitely have friction. Turning on a light bulb. Electrical. You've got the switch, you've got the wires to light. So you've got electrical energy to light energy. Well, how is energy lost or transferred? Heat from the bulbs. Using a nuclear reaction to produce heat. That's nuclear to thermal, and heat from the reaction is where the energy is lost. A rock rolling down a hill. Well, the rock started out at the top of the hill, so that's potential. It starts rolling down the hill, that's your kinetic energy. So where's your energy lost? The rock hits other rocks going down the hill, or it hits the surface of the hill. So there's your heat from friction of a rock against the earth. Now let's look here, see if we understand what we're looking at. Write the appropriate energy transition in the space provided. In this picture, it's kind of difficult to figure out what you're actually looking at here. I think that is some form of cereal bar. Okay, so if that is some form of cereal bar or something that you would eat, and then the bicyclist or the person is on the bicycle exercising. So what are the energy transitions that are happening here? The food provides the body with chemical energy, and then the person is able to ride the bicycle, which requires mechanical energy. So chemical energy to mechanical. So right here you would say chemical You've got the sun and the tree, or the tree growing. The sun and the tree. So what effect does the sun have on a tree? What type of energy does the sun have? If you go back to your examples from earlier, when you were looking at here, these right here, which one has the sun on it? For sun, do you go with radiant energy or do you go with nuclear? What's happening with the tree? Is that simply light energy, or is it your nuclear energy? Okay, we highlighted this one earlier. And here we have a plug. If this is plugged in, then what are you going to be able to do? There's the plug. This is your oven, your stove. So your plug represents electrical energy. And then you're going to be able to cook, which provides what type of energy? So here we're going to have, electrical through the plug. To what? Over here with the oven. It's an oven, so you know it's going to be thermal energy. Okay. Now, this activity, it says read the following scenarios and determine what kind of energy transition is being described. Example, Maurice applies the brakes to slow his bike. Answer, applying the brake introduces friction, which helps Maurice convert the mechanical, kinetic energy of motion to thermal energy at the point of contact between the brake and the bike wheel. A cornstalk grows 3 inches in 1 day. What kind of energy transition is being described? Susan lights a candle. Okay. I can go back to the match on that one. The match has stored chemical energy. You light the match. That's your thermal energy. And when you light the candle, there's your light energy. The Mars rovers are powered by solar cells. What kind of energy transition is being described? Tanya talks on the telephone to Olivia. Okay, talking on the telephone, that's got some electrical energy. You've got some sound waves going on there. So what was that in our... the sound energy? You're talking on the phone. So right here, Tanya talks on the telephone to Olivia. So talking is mechanical. It's also sound. And you have the cell phone, which is your electrical and your chemical. Okay, so there's a lot of stuff going on there. Now, Chapter 7 review. You have these 5 questions, folks. You have those 5 questions. You're in Google Classroom, and you are going to answer these 5 questions. Number 1, beating a drum represents what kind of energy conversion? When you beat a drum, that's what kind of energy conversion? Number 2, a car uses gasoline for fuel. Which of the following describes the energy conversion from gasoline to the movement of the car? We've highlighted that one. We talked about it, and then it brought it up again. Number 3, which of the following is an example of electrical energy being converted to light energy? Which of the following is an example of electrical energy being converted to light energy? Number 4, which of the following uses mechanical energy to function? I mentioned the answer to that one accidentally whenever we were, well, not accidentally, on purpose, but I didn't know that it was a question later. When we were looking at the forms of kinetic energy, I mentioned that. So, which of the following uses mechanical energy to function? Number 4 and number 5. An engine converts 95% of energy input into useful work output. What happens to the remaining 5% of the energy? Okay, well, we read something about that earlier, about energy that is lost, and it's not actually lost. We talked about what's happening to it. There was a whole heading on it, and it was right here, this whole page. Thermal energy loss, this paragraph, and then these examples. So the question is, an engine converts 95% of energy input into useful work output. What happens to the remaining 5% of the energy? Okay, so you should have answered these questions now. I will say that it is very important that you remember the law of conservation of energy. Conservation of energy here. Energy may be transformed, changed from one form to another, but in the end, you always end up with as much energy as you started with. The law of conservation of energy, which simply says that energy can neither be created nor destroyed. When we use energy, it doesn't disappear. We change it from one form into another. So be careful with those answers. Thank you, guys. I do hope that your behavior has been excellent for the substitute and for Miss Mullis. Remember, I'm still in the building. I love you guys. And I hope that you've been on your very best behavior. I hope that you got all the way to this point in the video where you are able to hear me actually speaking to you. You're good kids. Do me proud, okay? Just be sweet. Don't leave a mess. And last block, please, for the love of all that is holy, plug up the Chromebooks. Last block, 7th period. Plug up those Chromebooks. Thank you. I'll see you guys tomorrow.